Welcome to the Part 1 Engineering Graphics, the universal language of engineers and designers. It's more than just drawing. It's a critical skill that bridges the gap between conception and construction. Engineering graphics, also known as technical drawing, is a specialized language for engineers and designers to communicate ideas, designs, and technical information accurately. It serves as the foundation for all engineering disciplines and acts as a universal medium for conveying design concepts. This technique is crucial in clearly communicating engineering ideas, bridging the gap between conception and construction, and aiding in the visualization of designs and structures. Drawing equipment and instruments are fundamental tools used to communicate and realize technical ideas and designs in engineering. The drawing board provides a stable surface for securing the drawing sheet, allowing precise and detailed work. The T-square is crucial for drawing accurate horizontal lines and serves as a base for setting triangles. Set squares, also known as triangles, are used to draw inclined lines at specific angles, essential for creating precise geometric shapes. Compasses are used to draw arcs and circles, while dividers mark equal distances or transfer measurements. Together, these tools form the backbone of engineering graphics, enabling engineers and designers to create detailed and accurate drawings. Essential drawing equipment and instruments play a crucial role in precise and accurate technical drawing. A protractor is used to measure and draw angles, while rulers and scales serve as straight edges for drawing lines and creating proportional drawings. French curves are essential for drawing smooth, intricate curves. Drawing pencils come in various grades, such as HB and 2H, providing different line thicknesses and shading. Erasers and sharpeners are indispensable for correcting errors and maintaining pencil points. Lastly, standard drawing sheets come in sizes like A0, A1, A2, A3, and A4, providing the canvas for all these tools to work together in creating detailed and precise engineering graphics. Engineering drawing conventions are standardized practices that ensure uniformity, clarity, and ease of interpretation. These include orthographic projections showing top, front, and side views, specific line types representing different features, standardized symbols for welds and materials, and consistent format layouts. Mastering these conventions is key to creating professional, universally understandable technical drawings. In technical drawing, different line types communicate specific information. Continuous thick lines represent visible edges and boundaries. Continuous thin lines show dimensions and outlines. Dash thin lines indicate hidden edges, while chain thin lines represent center lines and symmetry axes. Thick zigzag lines are used for long breaks in components. Proper line usage ensures clarity and prevents misinterpretation of designs. The Bureau of Indian Standards, BIS, provides crucial guidelines for technical drawings. These standards ensure uniformity across engineering industries by specifying line thickness, style, and function. Each line type is carefully categorized, from visible edges to hidden details, creating a systematic approach to technical representation that professionals can understand universally. Technical lettering is the art of writing in engineering drawings, transforming text into a precise communication tool. Following the BIS standards IS 9609, 2001, engineers use a specific approach to make text clear and uniform. We prefer simple sans serif fonts like Gothic, with uppercase letters that ensure maximum readability. The size and spacing of letters depend on the drawing scale and sheet size, creating a professional and consistent appearance across technical documents. Dimensioning is the critical process of specifying an object's size, location, and features on a technical drawing. Think of it as giving a complete instruction manual for how a part should be manufactured. Engineers use 4 primary types of dimensioning: linear for straight measurements, angular for specifying angles, radial and diameter for circles and arcs, and ordinate dimensioning for referencing a single baseline. The key guidelines include using thin, continuous lines, placing dimensions outside the object's outline, and avoiding overcrowding to maintain clarity. Scale drawing is a powerful technique that allows engineers to represent objects proportionally, either reduced or enlarged to fit the drawing sheet. Imagine shrinking a massive building design to fit on a piece of paper or magnifying a tiny microchip component for detailed examination. We have 3 primary scale types: full scale, 1:1 ratio, reduced scale, less than actual size, and enlarged scale, greater than actual size. This approach facilitates the representation of objects of vastly different sizes while maintaining precise proportional relationships. Beyond basic scale concepts, engineers use specialized scale types for different purposes. Plane scales represent 2 units like meters and centimeters. Diagonal scales offer precise measurements. Vernier scales provide high accuracy for smaller units. Isometric scales ensure proportionality in 3-dimensional drawings. Each scale type serves a unique purpose, allowing engineers to communicate complex dimensional information with remarkable precision. Projection is the fundamental method of translating 3-dimensional objects onto a 2-dimensional plane. Imagine casting a shadow of an object onto a wall. That's essentially what projection does, but with geometric precision. Engineers use imaginary lines called projectors to transfer points and lines from a 3D object onto a plane of projection. This technique forms the backbone of technical drawing, enabling us to represent complex spatial relationships on a flat surface. Engineers employ 2 primary projection types. Perspective projection creates realistic images similar to human vision, with lines converging at a vanishing point. Think of how railroad tracks seem to meet in the distance. Orthographic projection, more commonly used in engineering, represents objects using multiple views like top, front, and side, maintaining true dimensions. This method ensures accurate representation without visual distortion. Orthographic projection uses perpendicular projectors to represent objects in 2 dimensions. The technique is categorized based on reference quadrants where the object is located. Imagine dividing 3-dimensional space into 4 quadrants, each representing a different orientation of the object relative to vertical and horizontal planes. This systematic approach allows engineers to capture an object's complete geometric information from multiple perspectives. Let's dive deeper into quadrant projections. In the first quadrant, an object is in front of the vertical plane and above the horizontal plane. Its front view appears above the top view. The second quadrant places the object behind the vertical plane, but still above the horizontal plane. Each quadrant offers a unique spatial relationship, helping engineers precisely map an object's position and orientation. Projecting a point might seem simple, but it involves carefully representing its position on horizontal and vertical planes. A point can be above or below the horizontal plane, in front of or behind the vertical plane. By mapping these positions, engineers can precisely locate a point's coordinates in 3-dimensional space. This foundational skill becomes crucial when dealing with more complex geometric representations. Sometimes, standard horizontal and vertical planes aren't enough to fully represent an object. Enter auxiliary planes, additional projection surfaces parallel to the main planes. These help engineers project objects not aligned with principal planes, providing clarity for inclined or skewed surfaces. By introducing these supplementary perspectives, we can capture geometric details that might be invisible in standard projections. Calculating the distance between 2 points in three-dimensional space is a fundamental skill in engineering graphics. We use the three-dimensional distance formula, which is an extension of the familiar Pythagorean theorem. By taking the square root of the sum of squared differences in x, y, and z coordinates, engineers can precisely determine the spatial relationship between 2 points. This calculation is crucial for understanding geometric relationships, designing structures, and solving complex spatial problems. Let's walk through a practical example of point projection. Consider a point P with coordinates 5, 4, 0. When we project this point onto the vertical plane, its vertical distance is 4 units. On the horizontal plane, its horizontal distance is 5 units. This simple exercise demonstrates how we transform a three-dimensional point into two-dimensional projections, a key skill in engineering graphics that allows us to represent spatial information on a flat surface. Projecting lines is a critical skill in engineering graphics. It involves representing a three-dimensional straight line onto two-dimensional planes, specifically the horizontal plane, HP, and vertical plane, VP. This technique allows engineers to analyze the spatial orientation and dimensions of a line from multiple perspectives. By understanding how lines project onto different planes, we can accurately describe and communicate the geometric characteristics of linear elements in technical drawings. Let's explore our first line configuration, a line parallel to both horizontal and vertical planes. In this unique scenario, both the top and front views show the line as a straight line parallel to the x-axis. The most remarkable characteristic is that both projections reveal the true length of the line. This configuration provides a straightforward representation that maintains the line's original dimensions across different views. In this configuration, a line is parallel to one plane while being inclined to the other. When the line is parallel to the horizontal plane and inclined to the vertical plane, the top view appears as a horizontal line, while the front view shows an inclined line revealing its true length and angle. The reverse is also true. A line parallel to the vertical plane will have different characteristics in its top and front projections. Our most complex line configuration occurs when a line is inclined to both horizontal and vertical planes. In this scenario, both projections appear as inclined lines and neither projection shows the true length of the line. This configuration requires advanced techniques like auxiliary projection or rotation methods to determine the line's true length and precise orientation. It challenges engineers to think creatively about spatial representation. Three-view projection is a comprehensive method of representing lines by showing their front view on the vertical plane, top view on the horizontal plane, and side view on the profile plane. The process involves carefully drawing the projections of a line's endpoints and then connecting these points in all views. This technique allows engineers to analyze the line's inclinations and relative dimensions from multiple perspectives, providing a complete spatial understanding. True length represents the actual length of a line, which isn't always visible in standard projections. Angle orientation describes the line's precise inclination to various planes. Engineers use multiple methods to determine these characteristics, including rotation, rotating the line to parallel planes, trapezoidal methods, geometrically constructing the true length, and auxiliary plane techniques. These approaches ensure accurate representation of line geometry. Traces are the points where a line intersects projection planes. We have two primary types: horizontal trace, HT, where the line meets the horizontal plane, and vertical trace, VT, where it intersects the vertical plane. Finding these traces involves extending the line until it meets the planes and identifying the intersection coordinates. This technique helps engineers precisely map a line's position and orientation in three-dimensional space. Let's look at examples. In the first example, we have a line AB that is 5 centimeters long, parallel to the horizontal plane, HP, and inclined at 30 degrees to the vertical plane, VP. The top view shows this line as a horizontal line measuring 5 centimeters, while the front view shows it inclined at 30 degrees. In the second example, line AB is inclined at 45 degrees to the HP and 60 degrees to the VP. We begin by drawing projections of the endpoints using the given angles, then connect these projections to form the front and top views, accurately representing the spatial orientation of the line. Line projection techniques have wide-ranging applications in engineering. They're crucial for analyzing spatial geometry and design, representing structural elements in technical drawings, and calculating true dimensions for manufacturing processes. From architectural design to mechanical engineering, the ability to accurately project and understand lines is fundamental to transforming conceptual ideas into precise, buildable designs. Projection of planes is a fundamental concept in engineering graphics that involves representing two-dimensional surfaces in three-dimensional space. Imagine a plane as an infinite surface that can be positioned and oriented in various ways relative to horizontal and vertical reference planes. Engineers must understand how to project planes onto different views to accurately communicate their geometric characteristics. This skill is crucial for visualizing complex surfaces and spatial relationships in technical design. Let's break down the essential concepts of plane projection. A plane is more than just a flat surface. It's an infinite two-dimensional area extending in all directions. We categorize planes based on their relationship to reference planes, horizontal planes parallel to the ground, vertical planes perpendicular to the ground, and oblique planes that don't align with either. Understanding a plane's orientation is key to accurately representing it in technical drawings. Think of it like positioning a piece of paper in different angles. Each position creates a unique projection. Imagine a plane parallel to the horizontal plane, HP, and perpendicular to the vertical plane, VP. When we look at the plane from above, in the top view, we see its true shape and size. For example, if the plane is a square, we'll see the actual square in the top view. However, when we view the same plane from the front, along the VP, we'll see it as a straight line. This happens because we are looking at the edge of the plane, not its face. Conversely, if the plane is parallel to the VP and perpendicular to the HP, the situation is reversed. The front view now shows the plane's true shape and size, while the top view presents it as a straight line. This approach ensures that we accurately represent the plane's orientation in technical drawings, allowing for clear communication of design details. When a plane is parallel to the horizontal plane and perpendicular to the vertical plane, its top view shows its true shape and size, like a square seen from above. However, the front view will just show it as a straight line because we're looking at its edge. If the plane is parallel to the VP and perpendicular to the HP, the front view will show its true shape and size, while the top view will be just a line. This method helps us accurately represent the plane's orientation in drawings, making it easier to understand and construct designs. When a plane is inclined to both the horizontal plane and the vertical plane, it presents a unique challenge. Neither projection will show the plane's true shape or size. For example, if we have a triangular plane inclined at 45 degrees to the HP and 30 degrees to the VP, its projections on both planes will appear as distorted shapes. This happens because the plane is not parallel or perpendicular to either reference plane, making its true size invisible in both views. This method of projection helps accurately represent complex spatial relationships in engineering drawings, ensuring clear communication and understanding of the design. Our most challenging plane configurations occur when a plane is inclined to both horizontal and vertical planes, or is completely oblique to reference planes. In these scenarios, both projections appear as distorted shapes, and the true size of the plane is not visible in either view. Engineers must employ advanced techniques like auxiliary projections to reveal the plane's actual geometric characteristics. This complexity highlights the sophistication required in technical drawing and spatial visualization. We conclude our exploration of plane projection by discussing traces, the points where a plane intersects projection planes. Horizontal traces occur where the plane meets the horizontal plane, while vertical traces mark intersections with the vertical plane. Finding these traces involves carefully extending the plane's edges and marking intersection points. Beyond theoretical concepts, plane projection has profound practical applications. Architects use these techniques to design complex structures, mechanical engineers analyze component surfaces, and manufacturers ensure precise component integration. It's a testament to how fundamental geometric principles translate into real-world innovation. We've reached the end of this video. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.